voice okay Nandi?
Yes, sir.
Good evening, sir. Yes, sir.
So what was the last topic?
Open ball.
Open.
Open set. What is the definition of the open set? If the every point is the interior point, that type of set we call as the open set. Okay, so now today we'll discuss one more example on the open set. After that we will discuss the properties of the open set. Okay, now the previously we have seen the Euclidean metric and discrete metric. In the discrete metric, so every set is open set. Each and every subset of the X must be the open set. That means that every subset of the discrete metric space is always open, whether that is a singleton set or closed interval or open interval or semi-closed or semi-open. Every subset of discrete metric space is must be the open set. That is the previous. Now we'll take the one more example. So here I'm taking the continuous function on close interval 0 to 1. 0 to 1. I'm taking the two elements from this set f comma g. Here I'm assuming this set of all continuous function on closed interval a to b norm infinity is a metric space. Norm infinity means norm infinity of this f is the supremum of mod f of t, where t is belongs to closed interval 0 1. Okay, now so here they have given one set u is equal to h belongs to C such that this H is in between two sets F and G. Now we will check. So this set forms a open set or not. Okay, that means we want to collect all the functions in between this F and G. That forms a open set or not. We'll check. Now, so I'm taking suppose a set in between a function in between these two functions. Okay, assume this is the red mark. So this is the okay. So this one is the assume our h. Now around h just we will form a ball. So I'm taking the length is epsilon. Okay, so open ball around h. So that open ball is h comma epsilon. That is the f belongs to C such that d of f comma h is less than epsilon. That means now the norm infinity of this f minus h is less than epsilon. That means here we'll find a function in between this f and g. So this is the h. Now this one is the a interior because this open ball is total in lies in u set u. So this h is a interior point. That means you can take any function in between this. So from the u. So definitely that point must be the interior point. That means here each and every point is the interior point of u. So u is a open set. That is the conclusion. Okay, now here I am giving homework for you just to try to practice the problems. The first one is okay, and observe in the second one. Now u is equal to h belongs to C such that f of t is less than or equal to h less than g. Here less than or equal, so less than or equal means it is not a, here not each and every point is an interior point, so this is not a open set. Similarly this one is the open set because less than, but the fourth one is not because here the less than or equal. Okay, so anyway try. Now we will compare the in the real analysis, that means the usual metric, real analysis, real analysis, that means the usual metric. usual metric, and the metric space, general metric. Okay, now first of all, in the reanalysis and the usual metric, now E neighborhood. So E neighborhood means E neighborhood is x such that mod of x minus a less than epsilon. That means it is the a open interval, and always this one is the open set. Here the open intervals in the real analysis in the usual metric. So E neighborhood is nothing but open interval, that is always is a open set. Now come to in the metric. So here we call it is the E neighborhood, we call it the open ball. Open ball. So center is A and radius is epsilon. Now we call it is the open ball. So this open ball is always is the open set. That means E neighborhood or open ball is always the open sets. That is the first one. Next one. Suppose A and B both are the open sets. So I'm taking the open interval 0, 1 and open interval 1, 5. I'm taking the intersection of these two. Intersection of these two is 1, 1, open interval 1, 5. That means what is the conclusion? The intersection of two open intervals again an open interval in the real analysis. Same here. The metric space also same, it satisfies. Suppose here A and B both are the open sets. Also open sets, whether that is a discrete metric or any other metric. Definitely the intersection of open intervals again a open interval. That is general. Next one, not only two, we can take the n number of open sets. That means the finite intersection of open sets always is a open set. Finite intersection of open sets always is the open set. Same in the metric also same. Suppose a1 up to an are the open sets on metric x comma d. The finite intersection of this a1 to up to an is again a met open set. That means the finite intersection of open sets again a open set. Okay, that is third one. Next one, come to the fourth one. This one related to the intersection. Now it is the only finite. Now I'm taking the orbit intersection. Now orbit intersection. So before going to orbit intersection, now I'm taking the a example. So one example. So a1 is minus 1 to plus 1, a2 is minus 1 by 2 plus 1 by 2, a3 is minus 1 by 3 to plus 1 by 3. Now I'm taking the infinite arbitrary intersection of this all the sets. Orbit intersection here gives the intersection of I is equal to n is equal to 1 to n, now 1 to infinity, and minus 1 by n to plus 1 by n. Now this arbitrary intersection gives the only single term set. Single term set. So single term set means now, so here each and every set is the open set, but the intersection is the not open set. That means the conclusion is finite intersection of open set must be the open set, but the arbitrary intersection of open sets need not be the open sets. Same in the metric space also it satisfies same. Example also same. So same here in taking the usual metric. So this is example of usual metric. This is also one type of metric. So here I am taking the usual metric. So usual metric it fails, but in the discrete metric it satisfies. Okay, usual metric. So here the a1 to up to an, the intersection is the single term set. So single term set is a not open set in the usual metric, but in the discrete metric, the single terms is always the open set. That means, so according to the metric, it will sometimes give the open set, sometimes not. That means the arbitrary intersection of open sets need not be the open set. Same in the real analysis. Okay. So finally, what is the conclusion? Finite intersection of the open set must be the open, but arbitrary intersection will not. So this is related to the intersection. Now, same will take the version in the union version. So union is, suppose A and B both are the open sets. Now I am taking the union of these open sets is always the open set. Same in the metric also same. Same two sets, not only two sets, I am taking the n number of sets. So finite union of open set must be the open. But arbitrary union of the open sets, open or not, it is the always open in the real analysis. Same in the metric also same. So how can we remember this one? Very simple. So intersection and union. This one is like a open, and this one is the close, not open. So ఇక్కడ ఏంటంటే arbitrary union work, arbitrary will work, but here arbitrary will not work. It is the only finite version. Okay, like that you can remember. Okay, same ఇక్కడ closed sets కూడా same వస్తుందండి. So intersection arbitrary intersection of closed must be the closed, but the arbitrary in closed sets must be the need not be the closed sets. Same exactly opposite. Okay, ఇలా గుర్తుపెట్టుకోవచ్చండి, easy. Open sets. So open symbol like this, it is the union is nothing but open symbol, and the intersection must be the closed. So simply just remember like this. Suppose AIs are open sets. Open set, now it is the open. Union means the open symbol. That means arbitrary, it will work. That means the arbitrary union of open set must be the open. Okay, but arbitrary intersection, it is not a open because the intersection not open, so arbitrary will not work, only finite will work. Same come to the closed version. In the closed sets A1 is the closed sets. Now the arbitrary intersection of the closed, this is the closed because intersection closed, so it is always the closed sets. But arbitrary union will not work because arbitrary union, it is the open set. Open union means is the open symbol, so it will not work. Okay, like that you can remember. So next one, in the real analysis, suppose A is the open set. That open set we can write the union of open interval. For example, A is equal open interval 1 comma 4. That means this A we can write 1 comma 3 union 2 comma 4. Similarly, say 1 comma 3 union 2 comma 3.5 union 3 comma 4. So these all are the open interval. That means if A is any open set, definitely it's that set must be, we can write the union of open interval. Same the metric space also same. Suppose A is a open set on any metric space, that A can be written as the union of open balls. Okay, so this one is the properties of the open set in the metric. Okay, don't confuse, same like the real analysis. Next one. Okay, now this one is important statement, so they will give the question on this statement directly sometimes. Okay, so here now before going to the statement, now just see the here the Venn diagram. Suppose x comma d is a metric space. Suppose here I am taking the A is, suppose x and y, I am taking the two distinct points which are belongs to the x, Suppose if there exist a two open sets around x and y, which are the disjoint sets, the type of property we call is the Hausdorff property. You can take any 2 points from the metric space. Around these 2 points, just if you can form the disjoint open sets, that metric satisfies the Hausdorff property. For example, here I am taking the x comma d is the discrete metric. I am taking the two different points from this one. Suppose I am taking the x and y. So around x, I am taking the A open ball, so with radius 1 by 2, and around y also I am taking the open ball, so with distance is 1 by 2, so 1 by 2 or 1 by 4. Observe here these two, so this one is a single term set, first one single term set. Observe these two are the disjoint set because here x is not equal to y, so it satisfies. That means the Hausdorff property satisfies discrete metric. So discrete metric always satisfies the Hausdorff property. Okay, that is the Hausdorff property. Okay, now this one related to the open sets. Similarly, same we will discuss the closed sets. So open sets from the interior point. So before going to the open set we have to discuss the interior point. Similarly same for closed sets. So before going to the closed sets we have to analyze the limit point concept. So open sets is related to the interior point and closed sets related to the limit point. Okay. Now, so interior point means what is the definition of the interior point? Suppose here a point around, so A just form a open ball or open interval. If suppose this open ball or open interval is total is inside A, this inside capital S, okay, S, this small a is we call it as the interior point. That is okay. But limit point concept same. So a minus epsilon plus a plus epsilon intersection of AC suppose non-empty. Then we call as a is small a is the limit point of, so a is limit point of S. Okay, in the real analysis, what is the real analysis? Suppose a is said to be is the limit point of S. For every epsilon greater than 0, there exists a minus epsilon to a plus epsilon. Intersection must be the non-empty. That type of point we call as the limit point. For example, I am taking the open interval 2 comma 4. Open interval 2 comma 4. You can take any point in this interval. Suppose I am taking the around 2 interval. So around 2 I am taking the interval. Around 2 I am taking the interval. That means, so 2 minus epsilon, 2 plus epsilon. Now intersection of this, yes, S means here the 2 comma 4. Always it is a non-empty because right side must be the inside. So this 2 is a limit point of S. Similarly 4 also limit point. That means here the each and every point is the limit point including the 2 and 4. That is the derived set. So derived set is nothing but set of all limit points of S equal to the derived set of S. Similarly, the derived set of closed interval 2 comma 4 is again closed interval 2 comma 4. Okay, నిమిషం అండి. Oh my God. Okay, so next one I'm taking the S is equal to natural numbers. So S is equal to natural numbers. Now we'll find the limit point of this. So this n, here there is no limit point of this n because you can take any point on the natural numbers, just form around, so interval around the point, suppose 1. So the intersection is always empty only except to this one. So here there is no limit point. So the derived set of this natural numbers must be the empty. Similarly, same for the integers also same. The derived set of integers must be empty. Similarly, rational numbers. The derived set of the rational number always is the real numbers. Similarly, the derived set of irrational numbers also real numbers. The derived set of real numbers must be the real numbers. For these three sets, the derived set must be the real numbers. That is the conclusion. Same here. Same concept in the metric. Same. Suppose x comma d is any metric. So a point is said to be the limit point of S. For every epsilon, there exists a ball, but means here the open interval. A minus epsilon to a plus epsilon. Here we call it as the open ball. So B of a comma epsilon intersection S A, it is must be the non-empty. Non-empty. So we call that point is the limit point. And the what is the definition of the derived set in the real analysis? Set of all limit points we call the derived set. So set of all limit points of S is called a derived set. So symbolically we will write the D of S. So these all are the derived sets of the given S. Okay. Open interval, derived set of open interval, closed interval, derived set of the closed interval, closed interval, derived set of the natural numbers and integers must be the empty sets. The derived set of rational, irrational and real numbers is the real numbers in the usual metric. But in discrete metric that is a different. We'll compare with the usual metric as well as discrete metric. Now come to the, so this left side is the related to the usual metric. Already we know that if it is the open interval, the derived set of open interval is the closed interval. The derived set of the closed interval must be the closed interval. The derived set of the finite set and integers and natural numbers must be the empty set. The derived set of rational, irrational, real numbers must be the real numbers in the usual metric. Usual metric space. But now come to the same sets in the discrete metric now. So before going to the discrete metric, now observe here. If the ball a comma 1 by 2, so a is the point and 1 by 2 is the radius, it is always single term set. And ball a comma 1 is always single term set. And ball a comma 3 by 2 is the R only, because in the discrete metric. That means if the radius is less than 1, that is single term set. If it is greater than 1, it is the total entire set. Now I'm taking S is equal to open set, open interval 2 comma 4. Now what is the derived set of this one? Derived set of this one, how can I identify? So first of all, we want from the, for every epsilon there exists a ball a, that means the ball a comma epsilon intersection S is, it is always, it is the non-empty. Sometimes there is a empty also, because observe, if it is epsilon is equal to 1 by 2 and 1, definitely it is the empty set only. If the epsilon is suppose 3 by 2, the intersection must be non-empty. So here there is no limit point. Similarly same for the closed interval also, there is no limit point. And the single term, sorry, finite set, no limit point. Natural numbers, integers, rational numbers, irrational numbers, real numbers. So for these sets there is no limit point in discrete metric, but in the usual metric that is a different. But in the discrete metric you can take any subset of S, there is no limit point. Same, now we will generalize. What is the generalization? Here we will generalize. Okay, yes, now we will generalize here. Suppose if x comma d is a discrete metric space, if x is a subset of x, the derived set is of S always empty. That means every subset of x has no limit point. Already in the previous also we have seen every subset of x is open set, and every subset of x is an interior set. Interior, that means each and every point is the interior point, but here each and every point is not a limit point. That is the difference between the limit point and here the interior. So here in the discrete metric each and every point is the interior point, but here each and every point is not a limit point. Okay, that is the observation. And the interior is related to the open sets and limit point is related to the closed sets. So what is the definition of the closed set in the usual metric? Just see here right side. In the right side, so we have the three types of the definition. The first one is S contains all its limit points, then it is the closed. Or the derived set of S is the subset of S, it is the closed sets. And the uh,
Complement.
complement of S, if it is open, that is the closed. Similarly in the open also same, the complement of the open, if it is suppose closed, then that is the S is must be the open. Okay, if S is open, definitely the complement must be closed. This is the if and only if condition. We'll write like this: if S is the open set, if and only if its complement must be the closed. Or if S is the closed set,
Its
its
complement.
complement must be the open set. Okay, but now I will not use this one, I will use the limit point concept. Okay, So the derived set is the subset of S, then it is a closed sets. In the open set, what this is the open set definition? Now we are taking the interior set is equal to A, but that is the open set. That means each and every point is the interior point, that is the open. Here the limit points is the contained in the entirely in S, it is the closed sets. Now we'll see the examples. The first one. So here I'm taking, we will take the in the usual metric, not in the discrete metric. The first one, S is equal to open interval 2 comma 4. What is the derived set? The closed interval. So it is not subset of S. So this S is not a closed set in the usual metric. Next one, S is equal to closed interval 2 comma 4. What is the derived set? Closed interval 2 comma 4 equal. So it is the closed sets. Next one, S is equal 1 comma 2 comma 3 comma 4. Derived set is the empty set. Empty set. So the derived set is the empty set and it is a subset of S. So this S is a closed set. Next one, S is equal to natural numbers and the derived set of S is equal to empty. So we know that, and subset. So finally the conclusion is finite set and integers and natural numbers. The derived set is the empty set. So derived set is a subset of S. So these all are the closed sets. Now come to the next one, rational numbers and irrational numbers. The derived set of rational numbers and irrational numbers are real numbers, but this one is not subset of the S. So these two are the not closed sets. Next one, S is equal to real numbers. The derived set of this real numbers is the real numbers. So a subset of S, it is the closed. So real numbers is always the closed sets. Not only closed but also open sets also. Okay, that means that in the usual metric, real number sets is the both open and closed, and rational and irrational numbers it is neither open nor closed. And this one is the finite set and natural numbers and whole numbers and integer always is the closed. And this one is the closed interval means is the closed set and the open interval means open set, that is okay. So this is the under usual metric. Now same topic will discuss in the metric. Okay, metric also same. So here S is said to be the closed sets if S contains all its limit points, or the derived set of S is S, or the complement of S is if it is open, S is the closed. Okay, now we will see the relation between the here the usual metric and discrete metric. Okay, so already in the left side already we know the results. Open interval 2 comma 4, it is not a closed set in the usual metric. Closed interval 2 comma 4, it is a closed set in the usual metric. And the finite set and integers and natural numbers, it is the closed sets in the usual metric. Next one, rational and irrational number, it is not open, that means neither open nor closed. And the real numbers, it is the closed sets. But come to in the discrete metric. In the discrete metric, so first of all, what is the derived set of this all? So the derived set of this all set is the empty set. So this empty set is the subset of S. That means these all are the closed sets.
Yes, it's it.
Closed sets. Closed sets. But already we know that in the discrete metric, subset of discrete met discrete metric space always the open set. That means here the conclusion is, so here the each and every subset of discrete metric space both open and closed, that is the conclusion. Is an end conclusion. Okay, now the note is the here x comma is the discrete metric space. If S is a subset of S, definitely that is the closed set. That means every subset of X is always is the closed. Same if every subset of X is open also. That means every subset of X both open and closed. But in the usual metric, only two sets we have the both open and closed. What are those? One is the empty set and another one is the real numbers. These two are the both open and closed set. But in the discrete metric, that is a different. Every subset of X is both open and closed. Okay, just if suppose in exam they will give the one question on particularly metric, so in that case you have to take the two metric, one is the usual metric and discrete metric. Just take the example and observe the property. Okay, then we'll get the direct answer. ఓకే, సో మీకు క్వశ్చన్ ఇచ్చిన వెంటనే జస్ట్ ఒక ఎగ్జాంపుల్ డిస్క్రిట్ మెట్రిక్ నుంచి ఒక ఎగ్జాంపుల్ యూజువల్ మెట్రిక్ తీసుకోండి, మీకు ఈజీగా ఆప్షన్ అనేది ఎలిమినేట్ అవుతాయి. ఓకే, నౌ ఒక్క నిమిషం. ఓకే, నౌ హియర్, నౌ దిస్ వన్ ఈస్ ద లిటిల్ బిట్ కన్ఫ్యూజన్. Yes, but observe. Suppose here I am taking the x is equal to close interval 0 comma 1, and I am taking the here this one is a usual metric. Usual metric, but in the usual metric I am not taking total entire real axis. I am taking the only close interval 0 comma 1. Now the first one, close interval 0 comma 1 open set or not? It is the open set, because you can take any point in this interval, that is the interior point. So here each and every point is the interior point, so that is the open set. Now same I am taking S is equal to closed, sorry, semi closed, that means the closed 0 and open 0.5. Now observe here, and now I am asking, is it a 0 is a interior point? So definitely interior, because here now just to form around 0 and interval, that means the epsilon neighborhood, that interval must be is the inside of this S. So this one is the 0 is the interior point, but we have the dot. What is the left side? Here there is no left side function, so left side points we have the points from the 0 to 1 only, so we'll take the interval only right side of 0. So in that concept, so 0 is a, so 0 is an interior point. Suppose if I am taking, suppose x is equal to minus 1 comma minus 1 comma 2. So in this case, so 0 interior point. Okay, okay, suppose if in this case, suppose if the x is equal minus 1 to plus 1 and s is equal to closed 0 and open, in this example, so 0 is not a interior point. Okay, so ఇక్కడ interior point అవుతుందండి, because here our x starts from 0 onwards, so that's why this 0 is the interior. But if the x is minus 1 to plus 1, so 0 is not a interior point. That is the observation. Okay, now just to I am giving the homework, just to try to practice the problems. Already have given the results also. X is equal to open interval 0 to 1, and I am giving the examples, 4 examples. So open interval and semi closed and semi open. So these all are the open sets, because observe here closed 0, so 0 is the interior point, and closed 1, so 1 also interior point, because this one. Next one, come to the closed sets. Closed sets, it is the regularly, it closed interval must be the closed sets. Next one is the neither open nor closed. So observe here the, it is the 0 is the interior point, but 0.5 is the not interior point, so it is not a open and not a closed also. Next one, so closed 0.21, so 0.5 is not a interior point and 1 is a interior point. Okay, so this one is the neither open and nor closed. So
Sir,
first
fourth one open, sir.
madam cheppandi madam.
Fourth one open, sir.
Yes
Ante
madam,
S
fourth
equal
one
to
is second one and fourth one both are the open, because our set x starts from 0 to 1 only. Okay. ఒకవేళ మనకు సెట్ ఒకవేళ ఇలా ఉందనుకోండి మేడం, x ఈజ్ ఈక్వల్ టు -1 to +1. సో ఈ సెట్కి మాత్రం దిస్ సెకండ్ ఎగ్జాంపుల్ అండ్ ఫోర్త్ ఎగ్జాంపుల్ ఆర్ నాట్ ఓపెన్ సెట్స్. అర్థమైందా మేడం? హలో
సార్ ఇప్పుడు సెకండ్ వన్ కి 0 అనేది
చెప్పండి మేడం.
0 అనేది ఇంటీరియర్ పాయింటా సార్?
ఎస్ మ్యామ్, 0 ఈజ్ ఇంటీరియర్ పాయింట్. వై? ఒక్క నిమిషం మీకు okay. So what is our x? Our x is closed interval
క్లోజ్డ్ ఇంటర్వల్ 0 to 1.
0 1. Now what is the definition of interior point?
If the neighborhood of a point
Yes.
completely lies in the set,
Yes,
then it is
lies
said
in
to be
the set.
interior point.
Suppose a minus epsilon and a plus epsilon is entirely x, that is the a is a interior point. Now come to it is the only it is our set. ఓకే, మన దగ్గర ఓన్లీ 0 to 1 ఉందండి మేడం, మిగతా ఏ పాయింట్స్ లేవు, అంటే అసలు ఈ లైనే లేదు. సో ఓన్లీ వీ హ్యావ్ దిస్ వన్ ఓన్లీ. ఓకే, now just 0 around 0 just form a interval. Now I am taking the epsilon is equal to 0.2 assume. So 0.2 means right sides 0 plus 0.2. Left side ఉంటుందా మేడం?
No sir.
So where there is no here space, there is no space.
Yes sir.
So there is no space. Now it is our ball, open ball.
Okay.
This open ball is now 0 to 0.2, closed 0 to open. It is now subset of
Closed interval 0, 1.
వర్కౌట్ అవుతుందా మేడం?
Yes sir.
Same, suppose if I am taking x is equal like this, -1 to +1.
Then it is not a
S
open
is equal, now same set తీసుకుంటున్నాం మేడం, ఇదే కదా మన సెట్, సేమ్ సెట్ ఇక్కడ తీసుకుంటాం. S is equal closed 0 to 0.5.
0.5. Okay.
Now ఇప్పుడు అవుతుందా మేడం?
No sir.
So that is the observation.
Okay sir. Okay sir.
Now here 0 ఇప్పుడు ఈ 0 ఇంటీరియర్ పాయింట్ అవుతుందా? 0 and
Yes sir.
0.5 ఇక్కడ ఈ సెట్కి మేడం, ఇక్కడ ఈ సెట్కి ఏమవుతుంది, మేజర్ సెట్ -1 to +1 అంటే సెట్ ఇక్కడ స్టార్ట్ అవుతుంది.
Yes sir. -1 to 1.
సో అప్పుడు ఖచ్చితంగా
And
ఈ లెఫ్ట్
0
సైడ్కి
is
వస్తుంది.
obviously it is an interior
ఎస్,
point.
ఇక్కడ ఏంటంటే జస్ట్ ఈ లెఫ్ట్ సైడ్ అనేది మిస్ అవుతుంది, రైట్ సైడ్. కాకపోతే ఇక్కడ ఏంటంటే లెఫ్ట్ సైడ్ సెట్టే లేదు, సో అక్కడ మనకు ప్లస్. ఓకే,
Okay.
సో ఇన్ దిస్
Okay.
కేస్ ఇన్ ద సెకండ్ ఎగ్జాంపుల్ 0 ఈజ్ నాట్ ఏ ఇంటీరియర్, బట్ ఇన్ ద ఫస్ట్ ఎగ్జాంపుల్ 0 ఈజ్ ఇంటీరియర్ పాయింట్. ఓకే, అది కొంచెం మనకి ఏంటంటే కొంచెం రియల్ అనాలిసిస్ పక్కన పెడితే అది మనకు పిక్చర్ వస్తుంది మేడం. మనం ప్రతిసారి ఏంటంటే ఓపెన్ ఇంటర్వెల్స్ని ఓపెన్ సెట్స్, క్లోజ్ ఇంటర్వెల్ అని అది పక్కన పెడితే అది అర్థమవుతుంది. ఓకే
Yes
మ్యామ్?
sir. Yes sir.
ఓకే, నెక్స్ట్ so that one is related to the open sets and the closed sets. Next one more concept. So after this concept we'll stop. Okay, now we'll come to the sequence. So before going to the sequence in the metric, now we'll observe the sequence in real analysis. What is the definition of the sequence, convergent sequence in real analysis? Suppose a sequence Sn in the real analysis, that means the real numbers, is said to be the convergence to L. For every epsilon greater than 0, there exists a natural numbers such that mod x n minus L less than epsilon. For every n is greater than n, or you can write this mod x minus L is less than epsilon means xn is belongs to the L minus epsilon to L plus epsilon for every small n is greater than capital N. What about that mean? So here the capital N is the fixed and small n is the varying. That means after nth term, after capital nth term onwards, the each and every term is in between L minus epsilon to L plus epsilon. అదే ఇక్కడ రాస్తున్నామండి. Okay, so xn plus 1, xn plus 2, so on, always in between L minus epsilon to L plus epsilon. Now geometrically also, just to observe here, suppose we have a sequence x1 x2 so on. Now this xn is tends to L means, now take the L, just to form around LA interval, so L minus epsilon L plus epsilon, just this interval covers all the points from n onwards. After nth term onwards, each and every point must be in between L minus epsilon to L plus epsilon, but 1 to n, maybe inside or maybe outside, we don't know. But after nth term onwards, each and every point must be the inside the interval. So that type of sequence we call it the convergence to L. So అదే ఇక్కడ రాస్తున్నామండి, mod x minus L less than epsilon for every small n. That means ఇక్కడ small n is greater than. So small n greater than means this small n is the varying and capital N is the fixed. After nth term, అక్కడ నుంచి జస్ట్ అంటే అన్ని పాయింట్స్ అని చెప్పట్లేదు. సో n onwards, this small n is nothing but maybe n plus 1 or n plus 2 so on. Okay, so that is under real analysis. Now same concept will take the in the real analysis. So in place of here the mod of xn minus L will take the open ball only here, because it is the e neighborhood. In place of this one we'll take the a e neighborhood. What about that means? Suppose we have the sequence x1 x2 so on so on, it is tends to L means, now just form around L there is a open ball with epsilon distance. Definitely there exists a suppose nth term, so nth term onwards each and every point must be lies in the ball only. అదే ఇక్కడ రాస్తున్నామండి. Suppose xn is the sequence in the any metric is said to be the convergence to L for every epsilon greater than 0, there exists a natural number such that d of xn L is less than epsilon. That means each and every point of the sequence belongs to the open ball after nth term onwards. That is the definition of here the convergence of a sequence in the metric. Okay, now we will see the properties of the convergent sequence in the metric. So same as the like the real analysis. In the real analysis, so now the first one, because I am taking the always usual metric, from the usual metric will give the conclusion. Suppose here there is a sequence, the sequence is 1 by n. So in the usual metric this 1 by n is tends to 0. Okay, that means in the real analysis every convergent sequence unique limit point. So same it will work in the metric also, because the metric, so usual metric is the one type of metric. Okay, so every convergent sequence always is a unique limit point. Next one, in the usual metric, that means the usual metric, sub 1 by n is the convergent sequence, always that is the bounded. So every convergent sequence must be the bounded sequence. That is also in the metric it will work. Next one, third point. So third one is, suppose there is a sequence xn is equal 1 by n, we know that tends to 0, but what I'm taking here the two subsequences. One is the even index, another one is the odd index. These two subsequences are tends to 0 only. That means here the sequence is converged to L, the each and every subsequence must be tends to L only. You can take the any subsequence, definitely that one also convergence to same point only. Okay, that is the third one. So same it will work in the real analysis also. same, third one. Okay. Same, if suppose one of the subsequence is not convergent to L, definitely the whole sequence is not convergent to L. That is the conclusion. Next one, already here we have seen. So even and odd terms. Suppose even terms are tends to 0 and odd terms are tends to 0, definitely the sequence must be tends to 0. If you are asking me. Suppose even terms are tends to L1 and odd terms are tends to L2. Different. So definitely that sequence is not convergent. But the even terms are tends to L and odd terms are tends to L. Definitely that sequence must be tends to L only. Even terms are tends to and odd terms are tends to different numbers. So definitely though those sequence are not convergent. Okay. Now we'll see the few examples in the usual metric and discrete metric also simultaneously. The first one I'm taking the R square D. So it is the Euclidean distance. Euclidean distance means Euclidean metric. That means D of x comma y is, so D of x comma y is equal to under root of x1 minus y1 whole square plus x2 minus y2 whole square. Now this is our Euclidean metric. Now here I'm taking here xn is the sequence. So sequence is the two tuples because in the R square. So one is the x1 dash, xn dash and xn double dash. So here this sequence I am taking is a convergence to P. P is also two tuples because the P belongs to R square and the first one is the P1 and second one is the P2. That means this sequence is converges to P1 comma P2. So definitely that the xn dash must be convergence to P1 and xn double dash must be convergence to P2. So this is the statement. Okay. So observe here the example. So 1 by n square and n cube minus 1 by n cube plus 1. The first sequence is convergence to 0. Second sequence convergence to 1. That means the whole sequence is convergence to 0 comma 1 only. Okay. Save. Next one. So we have a sequence xn. So this is the first sequence and this is the second sequence. The first sequence is convergence to 2 power 4 and second sequence is convergence to 0. So this whole sequence is convergence to 2 power 4 comma 0. Next one, this is the direct one. Suppose x comma d is the a metric space and xn and bn the two sequences. Suppose here an is convergence to a and the bn is convergence to b. So the combination, the distance of the d of an and bn also converges to d of a comma b only. So next one more concept here. So same like the real analysis, but in the real analysis, so what is the definition of the Cauchy sequence? The Cauchy sequence definition is the for every epsilon greater than 0 there exists a natural number such that mod of xn minus xm is less than epsilon for all n, e, n and m is greater than n. Same as the previous one. In the previous one, just around L, just a form interval. After nth term onwards, each and every term must be in between the interval. That means L minus epsilon, L plus epsilon. But here this is one is the little bit different concept. After nth term onwards, the distance between n and m always is less than epsilon only. This one. Okay, same here. The metric also same. Suppose here xn is the sequence is said to be the Cauchy sequence. If for every epsilon greater than 0, there is a natural number such that the distance between the xn and xm always is less than epsilon only. Okay. After nth term onwards, the distance between the each and every term must be less than epsilon only. Okay, now come to the properties in the real analysis. In the real analysis, so this one is the most important observation in the real analysis. If the okay, first of all, see the example. Suppose here the xn is equal to, I am taking the 1 by n. This tends to 0. And the xn is equal to 1 plus 1 by n whole power n. It is tends to e. So observe here. Here every Cauchy sequence must be the every convergent sequence must be the Cauchy sequence, and every Cauchy sequence must be the convergent. But I'm taking suppose different metric. So q and du. If it is r and du, so usual metric under the real numbers, okay, it will work. But if I am taking usual metric under rational numbers, so this 1 plus 1 by n whole power n, this one is the Cauchy sequence, but this one is tends to e. So this e is not belongs to q, because e is the irrational number. So this is not a convergent sequence in the rational numbers in the usual metric. That means in the real analysis, okay, so every convergent sequence must be the Cauchy sequence, but the converse, if the Cauchy sequence need not be the convergent sequence, that is in the metric space. Okay, okay. The conclusion is sequence is convergent, definitely Cauchy sequence, but the Cauchy sequence is need not be the convergent. Okay, in the metric space, but in the real analysis it will work. Cauchy is convergent also work, but in the metric it will not work, because here we have the different sets. That is the conclusion. Now so just see the this example, the first example, just three examples. The first one, so here the q and q comma du, that means the usual metric. So this one is the this is one is okay convergence to e, but e is not belongs to q. So this one is the not convergent in q. But the first one, this second example is the convergence to 0. So 0 is belongs to real number, so Cauchy sequence. And the next one, suppose if I am taking the suppose x is equal open interval 0 comma 1. So this 0 is not belongs to x. So it is not a Cauchy sequence, but it is not convergent sequence. So అక్కడ కొంచెం మనం అబ్జర్వ్ చేయాలండి. ఓకే, okay. So we know that already convergent sequence always the bounded, but the what is the converse? Bounded sequence, it need not be the convergent. So this is the direct one. Already we have seen the in the previously in the real analysis. Okay, every convergent sequence must be the bounded, but every bounded sequence need not be convergent, because one of the examples, suppose xn is equal minus 1 power n, so it is the oscillating, not convergent. Next one, Cauchy sequence. Every Cauchy sequence must be the bounded, but every bounded sequence need not be Cauchy sequence. This is also okay. Already we have seen. Okay. Now we'll combine all. So convergent sequence always Cauchy sequence. Cauchy sequence always bounded, but converse is need not be true. So bounded sequence need not be the Cauchy sequence. Cauchy sequence need not be the convergent sequence. Okay. So this just remember this relation. Every convergent sequence must be the Cauchy sequence. Every Cauchy sequence must be the bounded sequence. But every bounded sequence need not be the Cauchy sequence. Every Cauchy sequence need not be the convergent sequence. And every bounded sequence need not be the convergent sequence. Okay. So this one is the about the sequence and convergent sequence and Cauchy sequence. Okay. So now in the next class we will discuss the few more topics that is related to the complete metric space. Okay. Now anyway, now we'll stop now. So the remaining topic we'll discuss in the next class. Okay. Thank you to all. I will stop.
Thank you, sir.